That was so that I could talk about this last concept of filtering. I didn't feel like we got to do it in enough detail last time. So I want to pick up with this here. All right. Filtering is not going to be on exam 3. All right. The Fourier series and Fourier transform will be my focus. So you'll see when you see the practice exam, the type of question that I'm thinking about when I talk about the Fourier transform. But it's basically going to be, I'm going to give you a waveform. You should be able to probably graph the Fourier transform. Or from a graph of the Fourier transform, you should probably be able to tell me what the waveform is. Right? So just to make sure. So if I said to you something like what I have here, and I'll start recording. Oh, I am recording. If I said to you, I had a waveform like this. Let's say this is 10 and -10, and the height is 1, and the height here is 3. And I said this was x of omega. Okay, and I'd have to give you also an angle, right? So let's say this is 10 degrees, and this is -10 degrees. And this is something like that, okay? So from this, you should be able to tell me what x of t is, right? So according to this, at what frequencies do I have energy in this signal? According to that graph. -10, and what's the other one? 0. So it looks like if I just wrote this back, it looks like I have 3 plus e to the j 10 t, right? With an angle of, it looks like 10 degrees, plus what's going on with that -10 term? How would I express that in the time domain? What's that? Conjugate. So be, according to this, e to the -j 10 degrees, e to the -j 10 t. If I said, okay, give me that in terms of a cosine, how would I do that? So it'd be 3. I don't do anything to the 3, do I? It's a DC term. How do I turn e to the j 10 t? How do I turn this term and this term together into a cosine? What would that be? What's that? Euler's, yeah. So what would the amplitude of that be? Not 1.
Would it be 2 times cosine?
Yep, 2 cosine. Frequency would be 10. And what would the angle be? 10 degrees, like that. Right? So in other words, that basically is what I would call an inverse Fourier transform, right? Where I basically can look at that graph and I can relate that back to something that I would have in the time domain. Okay. All right, that's the basic approach. So we use this Fourier transform to be able to sort of simplify a lot of the analysis that we do. All right, so we're going to pick up on the filtering concept in a little bit more detail. So I gave this example. This is the kind of example that's going to be on the second project, where I say, all right, I'm going to have some sort of a waveform that is going into a system. And that system could be a circuit, or the example I was saying is if I've got a robotics sort of thing here, where what I have is I apply a voltage to a motor, okay? That motor, the differential equation for that motor would look something like this. So I said, I guess I have it written out here, but the output of this system is the speed of the motor, right? So the motor spins at a particular speed. The input to the motor is the voltage. And you can make a differential equation that relates to those things, okay? Now, what I have that I apply to the motor is a voltage, I said, that looks like this. So it's a square wave that that is repeating. And I said that what you do is you typically vary the what I call the duty ratio. In other words, you vary the percent of time that square wave is high. Sometimes it's maybe 50-50. In other words, it's high 50% of the time, low 50% of the time. Sometimes it's completely low. Sometimes it's completely high. So we say this duty ratio is what varies. So D is some number between 0 and 1. Okay. So what we said is that Vm of t is a periodic waveform. So if it's a periodic waveform, I can express it as a Fourier series, right? Which is to say that I can figure out what the specific values of the alpha n are. If you find yourself going, what the heck is he talking about? He talks about alpha n. Those are the specific values of the coefficients. Those are the specific amplitudes of the sine waves that need to be selected in order for those sine waves to exactly match up and fit into that waveform if I plotted it. So in other words, if I'm plotting everything properly, and I have the alpha n's properly, if I were to execute the command in MATLAB to generate this, my graph better look like VM right here. Okay. So from this, what we said is we can identify what we call a Fourier transform. That would be what I call VM of omega, right? And that has a formula in terms of what I call the impulses. The heck is VM of omega? It's a Fourier transform, but what is it? What is it telling me? Magnitudes and angles at the frequencies where I've got stuff, okay? And so we use that. In fact, technically you use that in 2112, you did impedance analysis. Basically what you're doing is you're saying, well, I had sine waves coming into this system at a particular frequency. So what's the amplitude and phase at those frequencies? And then let's figure out what effect the system has, in that case, the circuit has at those frequencies. And what you did was you figured out the Fourier transform of the output. Okay, so we're gonna apply that concept a little bit more generally, right? So basically, in general, the concept we have is something like this, right? So if I've got this picture here, all right, so I've got a differential equation that in this case, my output is V of t. My input is Vs of t. And what I said last time is if my input is a cosine like this, I can express it like this. What do I know about the output? V of t. If this is my input, Vs of t, what do I know the output's going to look like?
Has the same form as your input.
Has the same form as my input. So the way I write that is I say, well, this guy would be b e to the j omega naught t plus. I'm going to write this for the like this is I'm going to say this would be b conjugate over here, right? So this is my form of my output, and so I could express this guy like so. I could say v of omega, right? This guy has a Fourier transform. If I gave you this right here, and I said, give me the Fourier transform of that thing, all right? What would it be? I mean, maybe I should graph it first, right? Should I do me graph it first? So if I said, what does V of omega look like? What would V of omega look like for this thing? First of all, can I plot V of omega? I can't, right? What do I have to plot? Magnitude and angle, right? So if I said, well, let's plot the magnitude of this thing. What would the magnitude of this guy be? Well, wherever omega naught is, and at negative omega naught, what would I have at those frequencies? Yeah, I would have impulses, right? So this would be the magnitude of B, and this would be the magnitude of B. And then also I should draw a graph for the angle, right? And what would I see for the graph of the angle? What would I see at omega naught? Well, I'd see whatever the angle of B is. What would I see at negative omega naught? Angle in the opposite direction, because it's the conjugate, right? So this would be negative angle B. So the way we said we wrote this is said this V of omega, this Fourier transform. How do I put those two graphs? How do I put those graphs into an equation? How do those graphs get put into an equation? This is the kind of thing I would expect you to be able to do on a test, on exam 3. What would I write for those? magnitude of B, angle, e to the j angle B, and then I'd put in an impulse. Where would that be? Yep, omega minus omega naught. And then there would be B conjugate at omega plus omega naught, right? So that is the mathematical expression that's being graphed in those two sets of impulse graphs, right? So he says a complex function of frequency, right? So complex function of frequency means that I had to make two graphs. I had to do one for the magnitude and one for the angle. All right, so essentially with this whole idea, what we end up with, if I carry through this, is always the fact that I did sort of an example with first order stuff. All right, and I basically said if I have a differential equation that looks a particular way, and I have an input that has a particular look, then my output's going to have the same exact look. And we've done this enough times to know that if I plug in, if I have alpha 1 e to the j omega naught t as the input here, my output's going to have this form. If I plug that thing in, what I end up with is all of the e to the j omega naught t's go away. And I end up with this relationship that says this term here, this is from the input. This is from the output right here. And then I have this sort of thing that's relating them. So there's something I multiply the input by to get the output. Now, so this is from the input, this is from the output. How does this term right here in this box, how does that relate to the Fourier transform of my input? What do I have written here on this last line?
Coefficients.
Yeah, it's the coefficients. Specifically, what I've done is I've said this is the input coefficients. I should specifically say this is V of omega. Sorry, Vs was my input. This is Vs of omega at omega equal to omega naught. This guy here, this output piece, this is V of omega at omega naught. And then this thing that relates them here, this thing here is what I call the transfer function. And for a system, we say that, so this, in other words, I say this came from a system. In other words, there is some thing in the world, some physical thing that has a differential equation whose input and output are related through a differential equation. That thing could be a motor, that thing could be a circuit, right? But this guy is called a transfer function because it relates how an input and an output are related to each other. So that's the value of the transfer function specifically at the frequency omega equal to omega naught. All right, so carrying this through, basically for my first order example, what I ultimately see here is that if I call this thing the transfer function came straight away from the differential equation. And I see that what I can do is I can relate the coefficient of the Fourier transform of the output at omega naught to the Fourier transform coefficient of the input at omega naught and relate them through this thing called the transfer function. Okay. All right. So this is maybe the key thing to take away from. If I have a differential equation of this form, okay, the form that I have shown here, what I have is a transfer function that relates directly to that differential equation. And what do I see? So let's look at this here. Looks like the denominator of that transfer function is directly related to the coefficients in the differential equation. And then there's this j omega to the k thing. What the heck is this j omega piece here? Why do I have a1, which is the coefficient on the first derivative times j omega? And this guy right here, the kth derivative, gives me a j omega to the k. Where did that come from? Where did that come from? All the j omegas?
Did it come from the Fourier transforms?
What comes from, so when I plugged in e to the j omega naught t, every time I take a derivative of e to the j omega naught t, what comes down?
J omega.
J omega, right? And if I took 3 derivatives, how many times would j omega come down? 3. So if I keep this guy in general, the relationship that I get here is this transfer function should look like this, where I have the coefficients on the terms in the differential equation times j omega to whatever power that it came from in the differential equation. All right, so let's say, just for sake of argument, let's say you had d squared v of t dt squared plus 3 dv dt plus 2 v of t equals 3 vs of t. All right, and I were to try to write the differential equation for that, or sorry, write the transfer function for that. What I would say here is I would look at this thing and I would say my h of s, or sorry, careful, my h of omega. How would I write that for this differential equation? What would I have on the bottom? So I'd have a j omega squared. That's coming from this term. Plus 3 j omega plus 2. And there'd be a 3 on top. Okay. All right, so I get that relationship there. That is now that is effectively a Fourier transform that comes for the system. All right, you're going to learn more about that in 3111, but this really is the result of impedance analysis. And if you looked at what you did in 2112, you basically said, well, if I have a capacitor, I could say that the voltage is C, or well, the current is I equals C dV dt, or V equals I times 1 over j omega c, right? These things came from, if you look at those relationships, you'll see that what I'm doing here is I am applying, to get from this to this, I am applying basically this idea right here, right? The derivation of the impedance piece comes from this statement that I've got here. All right. The ability to do this is what you're going to need. You're going to need this in the project. You're going to need this to be able to solve problems 5 and 6 in the homework. Okay. It's a very useful way to be able to think about things. How do I get from a differential equation to something that I can analyze? So the whole idea of this, I've used this term filtering. So h of omega means that this system, and the system could be something like a motor, that the motor has some ability to do what I would call filter. So if I give it an input that has this form, all right, so I put a square wave into it. Square wave has infinitely many sine waves in it, but the motor doesn't necessarily respond to all of those sine waves because it filters them out. And understanding that concept requires us to be able to understand this idea of this sort of transfer function that comes from the system. Okay. All right. So basically what we end up with is, if you look at the differential equation, it has this general form. And I probably should say, I guess I could multiply this by some constant C naught, and that makes this C naught on top, right? That is one little caveat that's not caught by the way I wrote it there. Okay. All right. So if I have this relationship, so what I end up with here is that if I know the Fourier transform of the input, I can multiply it by the transfer function to figure out the Fourier transform of the output. Okay. And this is sometimes kind of thought of as you'll take signals and systems in 3111. This is what we think of when we talk about the system's viewpoint. In other words, if I have a transfer function and I have a particular input, then I know what the output's going to look like. I basically multiply the transform by the input. The amplitude of the output is the magnitude of the transfer function times the magnitude of the input. The angle of the output is the angle of the input plus the angle of the transfer function. Right? That is the basic idea. So if we wanted to, and we refer to this kind of analysis as frequency domain analysis, right? Because I'm not analyzing, there's no t's here in anything that I'm doing. I'm not using t's. I'm basically using the Fourier transform piece to say what magnitude and what angle do I have at each frequency, and then analyzing at those frequencies. Now, this is a tricky concept it's not that hard. I think once you start doing problems, it gets to make more and more sense. All right. So between now and Thursday, you definitely want to be able to make sure you understand that, because you're going to need to be comfortable with it into project 2. Okay. All right. So for the problems I have there, like problems 4 and 5, there's basically these kind of 4 steps, right? So if I have an input to some system, x of t, I need to be able to look at that x of t and get to the transform, okay? I need to be able to figure out the transform of my input. I need to be able to look at the differential equation, what I've called here the ODE, and figure out what is the transfer function h of omega for that system. Then I figure out the Fourier transform of the output using, h of omega times x of omega. And then I should be able to take that thing and reverse it into the time domain. So when I say reverse it into the time domain, meaning like what I did in the very, very beginning here today, if my output had a Fourier transform that looked like this, I should be able to walk it back into what it really is in the real world. Okay. All right, so it's those 4 steps. All right, those are the 4 steps that we're going to try to follow. Okay. All right, so what I did for today is I said, all right, well, let's look at an example which is pretty similar to, I think it's pretty similar to problem 5. All right, also similar to problem 6, but really similar to problem 5. Okay, so I have a circuit that has this differential equation, and I say this is my input, and I ultimately want to figure out the Fourier transform of the output. So I give you this signal. I want the Fourier transform of the input. I want the transfer function, and I want the Fourier transform of the output. And then we're going to make graphs. Okay. All right. So let's go through the process, and I want to follow it through, not necessarily in the order that I asked the questions, but I want to follow it through in the order of these steps. So the first thing I want to do is I want to say, okay, given my input, I want to figure out its transform. So Vn of t is this 5 plus 4 cosine 2 pi 60t plus 60 degrees plus 6 sine 2 pi 180t. So I got to figure that guy out. I got to figure out what his Fourier transform is. Okay, so now without going into details, right? This transfer function or this differential equation could have come from a circuit like this one. All right, so a circuit that has this behavior could have given me this differential equation, and in particular, in this case, I guess what I've said here is that Vn of t is equal to V out of t plus RC dV out dt. That's what I've given you in this problem statement. And the value of RC that I'm going to use is I'm going to say it has whatever that is, 1 over 2 pi 60, if you run those numbers. Okay. All right. So if I follow those steps, then I want to find the Fourier transform of the input signal, which means if my input is Vn of t, what I want to find is Vn of omega. All right, that's what I want to find. So if I give you this, how do I figure out what Vn of omega is? What do I have to do to figure that out? Yeah, I can graph the impulses here. So even before I probably graph the impulses, this one might be a little bit tricky because the impulses come if I have my cosines in that 2 rotating vector form, what I called approach 3, right? So how do I put this into that form?
Use Euler's identity first.
Okay, I would. So what would I do with the 5? Do I do anything with that?
Would that be multiplied by 2?
Well, if I have a constant, a DC term, I don't do anything with that.
Right.
That just stays. What do I do with this 4 cosine 2 pi 60t plus 60 degrees? What's my Euler tell me to do with that? So two rotating vectors. What's the easy part? What's the frequency of those two rotating vectors? What's that? One's 2 pi 60 and the other one is negative 2 pi 60. What's the amplitudes of the two of them? 4/2. And then they have an angle associated with them, right? So this guy's going to become plus 4/2 e to the j 60 degrees times e to the j 2 pi 60t. That's the positive rotating vector. What would the negative rotating vector be?
Plus 4/2 and then the conjugate.
Yep. 4/2 e to the negative j 60 degrees, e to the negative j 2 pi 60t, like that. Okay. And then, okay, then I have this sine term here. So does that mean it's 6/2 e to the j 2 pi 180t? No, because it's sine, right? What do I have to do to sine?
Minus 90.
Well, yeah, so
You
it
change
becomes,
it to
I
cosine?
subtract, yeah, I subtract 90, right? So it becomes 6 cosine 2 pi 180t minus 90 degrees, like that, right? And the way that I think about that one, if I really had to, is if here's cosine and here's sine, I would have to take cosine to the right by 90 degrees to match it up with sine, right? To go to the right means a negative shift, okay? So if 6 sine 2 pi 180t becomes this in the cosine form, help me out. What do I write for that one? In this formula here, what am I going to write for that one?
That's gonna be 3e to the power j minus 90
You got it?
and e to the j 2 pi 180t
Perfect.
and the conjugate of it.
Yep.
It's
And
gonna
then
be positive 90 and negative 2 pi.
you got it. Okay. Like that. All right. So if I look at this, that says if I think about I wrote this in kind of that Fourier series form. So what I've done is I've expressed this guy as alpha n e to the j n omega naught t, where this goes from n equals negative infinity to infinity. What values of n do I specifically have here? I have n equal to what? Yes, all n are possible. But in this case, which ones do I actually have? Looking at this waveform, what's the fundamental frequency? 2 pi 60, right? So looks like I have a fundamental and what harmonic number? Third. And then the DC term is at 0, right? So this guy goes from negative, I have n equal -3, -1, 0, 1, and 3. Those are the ones that I have that are non-zero, right? These are the ones where alpha n is non-zero. Everything else, alpha n is 0.
Can you repeat, I'm sorry, can you repeat how you get the n numbers again one more time?
Well, so in this case, I have omega naught. The fundamental frequency is 2 pi 60. So that's my fundamental 1 times omega naught. So my third harmonic, 3 times omega naught, is 2 pi 180. And my only other term I have is 0 times omega naught, or 0. And when I have it in this form, right, where I have the two rotating vectors, I always have to have the positive frequency and the negative frequency. That's where the negatives come from.
Oh, okay, thank you.
Yep. Okay. All right. So now I've got that. Now the question is then, how do I get that into a Fourier transform? Okay. So how do I get that into a Fourier transform? So let's do a graph down here. Or I'll do a graph over here. This is my formula for the Fourier transform, right? So what I do is at the frequencies where I have information, I have to try to draw a graph of this thing. So let's try to draw the graph. So there's two pieces. There's the magnitude of Vn of omega, versus omega. And then there's the angle of Vn of omega versus angle. Okay, so I have something at 0, I have something at 2 pi 60, and I have something at 2 pi 180, and at their conjugates. So negative, or their mirrors, I guess. Okay, so what would I draw here for this? Based on this is my Vn of t that we got on the previous slide, I just carried it over. How would I express the graph here? Where would I, so let's take DC first. What's the height of my impulse at DC?
It's 5.
Yep, it'd be 5. And technically it's not a height, it's an area, right? Although it's, and the only way we have to express it is by a height, right? What do I have at 2 pi 60? This guy would be 2, right? And this guy would be 2. And then if we look at 2 pi 180, our height would be 3. And at negative 2 pi 180, our height would be 3.
I'm sorry, like why is 2 and 3 over here? I'm just like, I missed that part.
Because you're saying, okay, so here's the amplitude at 2 pi 60.
Yes,
So it's 2 with an angle of 60. So I put a 2. And then if I did this at 2 pi 180, I would say the angle here on the angle graph is 60 degrees,
oh, okay.
right? And so if I looked at the negative, so this would be 2 pi 60. If I look at the negative 2 pi 60, that's this amplitude here. So what would I put for the angle at negative 2 pi 60?
That'd
What
be
would that
negative 60.
Yeah, that'd be negative 60. Okay. And then what would I do for 2 pi 180? Well, we said it was for 2 pi 180, the magnitude was 3, the angle is negative 90. So I go to 2 pi 180 and I do, this is negative 90. And then over here at negative 2 pi 180, what would my angle be at negative 2 pi 180?
It's gonna be a positive 90, which is gonna be going up.
Yep, it'd be positive 90. Okay. All right. Okay. So that is my result. How do I write that here in terms of the set of impulses? Well, I have a 5. At what frequency do I have 5?
0?
Yeah, so how would I write that as an impulse? Delta of what? Delta of omega. Because when omega is equal to 0, the impulse is going to be 5. Okay, and then I keep going. So if I just move from here to here, let's do the one at negative 2 pi 180. That would be 3 times an angle of 90 degrees. Delta of what? What would my delta be? So for negative 2 pi 180, what delta would I have?
There's gonna be omega minus, omega plus 2 by 80.
Yep, omega plus 2 pi 180. If I do the negative 2 pi 60, I see I've got a magnitude of 2, got an angle of negative 60 degrees, and it's located at negative 2 pi 60. So in my expression here, I would say omega plus 2 pi 60. And the way I can check this is if I plugged in omega equal to negative 2 pi 60, the argument becomes 0. And delta of omega should be equal to 1 when omega is 0. The thing to remember is if I have delta of x, that's 1 for x equal to 0, 0 otherwise. So think of it as kind of a general formula, right? Right, and then I can do the same thing at the other frequencies. So this would be 3e to the negative j 90 degrees at minus 2 pi 180. Okay. This says if I plug in omega equal to 2 pi 180, this argument here becomes 0. So this says this is the term at omega equal to 2 pi 180. and then I have e to the j 60 degrees. So 2 times e to the j 2 pi 60, or 2 angle 60, if you want to say it that way, delta omega minus 2 pi 60, like that. Okay. All right. That's the expression. I've got the Fourier transform now. All right. That you should be able to do for yourself for the exam. All right. That sort of process. Now, that's the first step in my process here. So I said, if I want to use this to solve, the first step is that I should be able to get to the Fourier transform of the input. Second step is I should be able to get the transfer function from the differential equation. So here, all right, this is my differential equation. And I'm going to say that this is, in this particular case, v out of t plus rc dv out dt. So I need to be able to write h of omega by looking at that differential equation. So what would that be here? It'd be something over something. What's on top? 1. What's on the bottom? If this is my form of the transfer function, what do I put on the bottom? What do I get for the v out of t term?
Just 1.
Yep. And what do I get for the RC times the first derivative?
J omega.
Yep. So I get j omega times RC. So that's my differential equation. And again, I'm going to plug in the number RC equals 1 over 2 pi 60. I'm just keeping it general. All right, for now. All right, so in other words, this guy here, this is a function of frequency. If I plotted this versus, and I ask you to do that in the homework, I ask you to make a plot of it. If I plotted the magnitude of this thing, what this guy's going to look like is something like this. If omega gets to close to infinity, or let's start at the easy end. If omega is equal to 0, what's the magnitude of this transfer function? If omega is equal to 0, what's the magnitude? 1. I could see that. If I plug in omega equal to 0, this guy simply becomes 1 over 1. Nothing complex about that. If omega becomes equal to infinity, I have 1 over infinity. What's 1 over infinity?
0.
0. So this guy's going to look like this. All right, where he should be getting closer to 0 than I'm probably showing. He should be more symmetric than I'm showing here. My MATLAB graph will show it better. All right. Now I'm going to talk about this at the very end today, but I call this a low pass filter. Why do you think I call this a low pass filter? For my omega values that are small, yeah, it allows stuff to quote unquote pass, right? If you think when I say pass, the term pass, what it means is that my input and my output at those frequencies would look the same. So if the value of this transfer function, because we're saying is v out of omega equals h of omega times v in of omega. What we're saying is if it passes, that means if the magnitude of h is close to 1, then the Fourier transform of the input and Fourier transform of the output would basically be the same. It's passing through. Whereas at a really high frequency, as I get close to infinity, h of omega is going to approximately be equal to 0. So no matter what input I put in, am I going to get an output? No. Right, so that would be, this is a low pass filter. Low frequencies make it through, high frequencies don't. Right, that's our concept. And we don't say they don't make it through. We typically, what we say is they are quote unquote attenuated, which means that they're made smaller. Right, so in the context of filtering, we'll say stuff passes or it's attenuated. Attenuated is to express the fact that it's reduced. Right. So in other words, if I put in 1 volt, maybe I only get a millivolt out. Right, that's the meaning of attenuating. Okay, so got my transfer function. My third step was to figure out the transform of the output. And what I got to do is I got to say v out of omega equals h of omega times v in of omega. And I got this big ugly thing here. All right. So what I could do is I could draw the graph of Vn of omega, which is just a bunch of impulses. And I could draw the graph of H of omega. So first of all, is this one equation here, what I've written? It's actually not, right? It's actually two equations, isn't it? They're all complex numbers. So what two equations do I have here? One complex number times one complex number is equal to another complex number. When you multiply complex numbers, what do? What's the right way to figure that out? I have one relationship for the magnitudes, and I have one for what? The angle. So what's the relationship for the magnitudes in this case? Multiplication of the magnitudes. V out of omega is equal to the magnitude of H of omega times the magnitude of Vn of omega. Okay, very simple process. What do I do for the angles? Yeah, Adam. The angle of V out of omega is equal to the angle of H of omega plus the angle of Vn of omega. Like that. Okay. And based on the way I expressed this guy before, Vn of omega's magnitude and Vn of omega's angle, I've already expressed those here in this graph. All right, so I've already got that covered. So what do I have to do? Well, I have to figure out the graph of H of omega. Now I'm going to go back and do this by hand here, but I'm going to skip ahead to where I'm done here at the very end. I don't think I can delete this because I put this in the notes that I posted. What I have in this graph, all right, is I've got two graphs specifically, right? What I have, the top here is the set of magnitudes, and the bottom is the set of angles. So what I've done is this red curve here, right? This curve. This curve right here, that's the magnitude of the transfer function. And then I've put in the impulses using that stem command. I put the impulses in that represent the Fourier transform of the input. Then for the yellow impulses here, I've put the magnitude of V out. How did I calculate the magnitude of V out? How did I calculate those? Well, I basically went through and I said, I did this equation. All right. But I have to, yeah.
Can I ask a quick question on this formula to the right? So your coefficients for where it's 3 over j, is that due to the fact that you didn't transform that into a cosine function?
Yeah. So if I think about 3 over j, that is negative 3j, or 3e to the negative j 90 degrees. Is what that is. I just wrote it without the e to the negative j 90.
Okay,
It's
gotcha.
the same. It's the same thing, right? Okay. All right. So to get the magnitude of V out, so what do I have to do? I don't have to figure out the magnitude of V out at every possible frequency. I only have to do it at what frequencies? Well, DC, 2 pi 60, 2 pi 180, negative 2 pi 60. Negative 2 pi 60 and negative 2 pi 180. All right, so I'm going to do it one at a time. All right, so let's start out with the easy one. The easy one would be at omega equal to 0. Okay, so we go back to these two formulas here. So if I say, what's the magnitude of V out at omega equal to 0? So I specifically just plug in omega equal to 0. All right, so I have H of 0 times the magnitude of Vn at 0. Okay, so my H of omega is this guy. 1 over j omega RC plus 1. What's Vn of omega when omega equals 0? Yeah, 5. All right, so this guy is 5. What's the magnitude of this thing when omega equals 0? Well, technically, I should do some math to compute a magnitude here, but It's actually not too hard. If I plug in omega equal to 0, what's h of omega become? 1, right? So I have the magnitude of the transform of the output at 0 is equal to 5. All right. So what I can do right now is I can convert that back into something in the time domain. What kind of signal do I have if at DC? What is that? Is that a sine wave at DC? What is it? It's a flat line, right? So that tells me that the way I'm going to write this is I can think of these sort of in parts. So V out DC is equal to 5. So I put 5 in and I get 5 out at DC. Now, if in MATLAB I asked you to graph that, right, or to put this into a function, I probably would have a function in MATLAB where I would say V out DC equals, I would say 5 times what do you think? Ones, yep. Ones. This is where I would do usually ones of size t, meaning I want to plot something the same size as my time vector, right? But it's going to be, to get a constant, I'm going to say 5 times ones. That's going to be a constant number 5. Okay. All right. So I'm going to keep going. Omega equal to 2 pi 60. So magnitude, first of all, did I have an angle to worry about here at DC? Okay. I don't here, but I could, right? What if I had -5 like that? What if it was a -5 instead of a 5? What would my angle be then? 180. Okay. So there's 2 possibilities, right, for a DC term. The DC term is a real number, right? So real numbers can have 2 angles, 0 degrees or 180, right? Those are both on the real axis. Okay. All right. So at omega equal to 2 pi 60. So I'm going to say V out of 2 pi 60. The magnitude at that point would be the magnitude at 2 pi 60 times the magnitude of the input at 2 pi 60. All right. So and we have that h of omega equals 1 over j omega RC plus 1, like that. Okay. All right. So what's the magnitude of V in at 2 pi 60, according to what I have here? What's that? That would be 2. Okay, that's the magnitude of it. What's the magnitude? How would I figure out this? The magnitude of h 2 pi 60. How do I figure out that? How would I figure out that? Okay, so yep. Magnitude of h of omega. Technically, I should be able to make a formula for this. So I have one complex number over another complex number. So 1, and then on the bottom, I get a square root. What's the square root of? If this is my h of omega over here, how do I write its magnitude? Square root of what plus what?
J omega RC squared plus 1 squared.
Well, you're close. Omega RC squared plus 1 squared. The J doesn't go into that. Okay. And you got to be careful about that, because if I had done J, if I had J squared, what's J squared always equal to?
Changes the sign and be negative.
-1. Yeah.
Yeah.
So you're just taking the imaginary part. All right. Think of that J as a basis vector, I guess, is the way we think of it. And that, like a X hat or a Y hat in a unit vector, like you would say in physics. Okay. All right. So in this case, what I would do is I would plug in omega equal to 2 pi 60. So I'd say h of 1 over 2, h of 2 pi 60. All right, equals 1 over square root of, okay, if you plug in the fact that I said RC is 1 over 2 pi 60 and omega equals 2 pi 60 means I'm going to get 1 plus 1 down there. All right, so I did a nice value to make some math easier for myself. So I basically get that this becomes 1 over the square root of 2. So my magnitude here, the magnitude of the output at this particular frequency is 2 times 1 over square root of 2. All right, now there's also an angle piece, right? So for the angle, I say angle of V out at 2 pi 60 is equal to what? How do I write that? Yeah, angle of H at 2 pi 60 plus the angle of Vn at 2 pi 60. All right, what's the angle of Vn at that frequency? So here's the term. What's the angle?
60?
Yep, 60 degrees. And then I got to plug into the transfer function and say, well, the angle of H of omega. All right, if this is my transfer function, how do I write the angle of that? What's the angle of 1 over a complex number? I say it's 1 minus the angle of the bottom, right? What's the angle of j omega RC plus 1? How can I express that?
That's
Tan-
1 minus 1.
Well,
Oh.
tan inverse of omega RC, the imaginary part over the real part, which if I plug in omega equal to 2 pi 60, right, I'm going to get H of 2 pi 60. If I plug in RC equals 1 over 2 pi 60 and I plug in omega equals that, this guy's going to work out to be negative 45 degrees. All right, is what I would work out, what that would work out to be. I got to be careful. I said 1 minus that. It's the angle of the top. What's the angle of the number 1? 0 degrees. Right. This guy would work out to be minus 45 if I went through that. So this is minus 45 degrees. So from that, I can say right off the bat here, the V out at 2 pi 60. All right, this guy is somehow relating to. It tells me how I can figure out the complex exponential at that point. This says the complex exponential would be 2 over square root of 2 times e to the negative j. So 60 minus 45 is what? 15. So e to the j 2 pi 15 degrees. And it happens at a frequency of 2 pi 60t. Okay. Now, technically, I should do the same thing at omega equal negative 2 pi 60, right? And when I do that, I'm going to get something that is 2 over the square root of 2 times e to the negative j 15 times e to the negative j 2 pi 60. So I say, I'm not going to bother doing that. What I'm saying is, and I ask you something like this in the homework, right? I say, all right, in the homework, tell me what's the amplitude of the corresponding cosine. So I basically say it ends up being 2 times, right? 2 times the coefficient that I just got here, right? So it would be 2 times, so that the cosine that I would get, would be, yeah, 2 times square root of 2, like that. So the amplitude of the cosine is twice as big. It's just Euler's identity coming into play there. Okay. So that is a question that I think I ask, right? Where I say here, what is the amplitude of the cosines at 60? Well, so you can tell and 180 hertz in my example. I took that straight from the homework, right? 60 and 180 hertz. Well, the amplitudes at those frequencies, all right, are just twice what I got out of this analysis here. Okay. I'm just skipping the negative frequencies because we know with the negative frequencies, it's just going to lead to twice the amplitude in the same angle, right? So you should be fairly comfortable with how Euler's identity gets you to this result by now. Okay, if you're not, you need to get there. All right, so what do I do at 2 pi 180? Well, I do the exact same process, okay? The exact same process. So the magnitude of h of 2 pi 180. I got to figure out what that is. Okay. And then I got to figure out the angle of h 2 pi 180. Right. Remembering that h is this function 1 over j omega, and I'll plug in RC as 1 over 2 pi 60. Right. Plus 1. All right. If I go through that process, I don't want to go through the math of it here. It's not that useful to go through. What is the actual values here? This works out to be, this way. It works out to be, so if I write it this way, h of 2 pi 180 becomes 1 over 1 plus j3. In other words, if I plug in 2 pi 180 into this expression, what you get is 1 over 1 plus j3. All right, so help me out. What's the magnitude and how would I get the magnitude and angle of that? If I told you this, how would I get the magnitude and angle of that? What's the magnitude of it? Be 1 over what? 1 over, yeah, the square root of 3 squared plus 1, or 1 over the square root of 10, like that, whatever number that is. And then what about the angle of that? Negative, so it'd be, so when I have two complex numbers like this, 1 over another, what's the angle of the top? 0, minus the angle of the bottom. What's the angle of 1 plus j3? How would I get that? Minus inverse tan of 3. All right, and if I worked through the math on that, it'd be negative 71.6 degrees. Okay, is what I would get. And 1 over,
I'm sorry, it's supposed to be 1 minus 10, right?
no, it's the angle of 1. So the angle of it would be, so the angle of 1 is 0. So it's 0 minus the angle of 10 inverse of 3.
Oh, okay.
Yeah. Okay. All right. So then I've got the magnitude, I got the angle. So I can say the magnitude of V out at 2 pi 180 is equal to the magnitude of H of 2 pi 180 times the magnitude of Vn at 2 pi 180. Okay. What's the magnitude of, according to what I've got here, what's the magnitude of Vn at 2 pi 180?
That's gonna be 3.
Yep. So this guy's going to be 1 over square root of 10 times 3. If I do the math on that, this guy works out to be 0.949, like that. And if I say, what's the angle of it? The angle of V out at 2 pi 180. Right, the angle of that would be whatever the angle of H is, plus the angle of Vn at that same frequency. So what's the angle of Vn at that frequency? What's the angle of
Minus
Vn?
90?
Yep, minus 90. And then I have this minus 71.6 to go with it. All right, that's the angle of H. All right, so this works out to be negative 160.6 degrees. All right, so that tells me this guy would, so at 2 pi 180, this would give me essentially a complex exponential that would have a magnitude of 0.949 with an angle of negative 160.6 rotating at 2 pi 180t. And if I looked at what I would get at the negative frequency, it would be the complex conjugate of that. And so that tells me that if I looked at the cosine that I got at 2 pi 180t, right, it would be 2 times 0.949 cosine 2 pi 180t. And what would be the angle? What would be the angle of that cosine? Negative 160.6. All right. So, all right. Then I basically at the end, what I end up with is this. And if I look at that, I can use that to quote unquote inverse transform it. That's my very last step. So I take these values and I inverse transform that to this expression. Right. So I kind of did that as I went. Right. But I'm saying I had the input that I had all the way back here. This was my original input. And I'm saying that my output will look like this. Now that may sound tedious, but it's a heck of a lot faster than having solved the differential equations, right? That's the part that's really messy and allows me to visualize some stuff. So what I ask you to do also, the last couple of steps there, is to graph it. All right, so here's an example. I had this in the notes before, but we can walk through this real quick in the time we've got left. Right, what I did was I defined an omega vector. In this case, it starts at -3 times the fundamental, increases in steps of the fundamental to 3 times the fundamental. So if you looked at what values were in my omega vector, what would be there? -3 times omega naught, -2, -1, 0, 1 times omega naught, 2 times omega naught, 3 times omega naught. And then what I did was I made my V in vector. And so what I did was this right here. This is my alpha -3. This is my alpha -2. This is my alpha -1. This is my alpha 0. This is my alpha 1. This is my alpha 2. This is my alpha 3. So I put them in order. Okay. And what I then did is I have this for loop here that is computing. You don't necessarily need to do this. You could have done what I just did by hand, right? Nothing wrong with doing that. You could do that, right? And for problem 5, you could do it by hand. What I did was a for loop, which looped through all my values of V in. And what I did was I said, so here, right here, this is my H of omega right here. So I'm basically taking my H at each frequency in my V in vector. I'm computing H in to calculate the Fourier transform of the output, right? And then what am I doing here? Well, I'm generating a vector for H. Now, a couple of things. I have this dot divide. Why do I have this dot divide? It's element wise because omega plot down here is a vector. And I want to generate a value of H at each value in that vector. So, I mean, I got to do a dot divide to do an element wise operation. And omega plot, so why do I have omega plot and omega? Well, because I'm plotting a lot of points here. I'm trying to plot a continuous function. So my steps are 0.1. My steps are much, much smaller than they are in this omega vector. Right. So I have to do that because my V in only has values at certain frequencies. My H has values at every frequency. Okay. So that's why I did that. So then this, you can follow my template here, but I end up with a picture that looks like this, right? Where I can see that my H is continuous. And then I can see that my impulses only happen at certain frequencies. Now, I said this is a low pass filter. We'll talk a little bit more about this on Wednesday. You don't need this for the exam, okay? But this idea of a low pass or high pass filter, we'll need that for the projects. We'll talk about that idea on Wednesday. If I look at this though, the idea is this is a low pass filter. The way I can check is it's passing low frequencies, meaning the magnitude is 1 at low frequencies, but the magnitude goes to 0 as omega gets to be a really big number. All right, that's the check you should do. And I have the definitions of that here. All right. All right, that's it.